So let's take this example. And the example basically says that, let us say we again have a inertial reference frame O, right? And let's say I have a container, right, in which I have hung a mass M connected to a massless string with its ceiling, right? And these are all the initial conditions, right? And this container itself is moving with an acceleration A with respect to the reference frame O, right? So now what we can do is, I will take the container also to be one reference frame, right? So somebody sitting on ground will see a mass hanging in this container, and the container accelerating towards, let's say, x direction, also x direction, with magnitude A, and somebody sitting inside the container, right, since it's moving with the container, will again basically see that everything is stationary because you are in that system. However, there are different forces which are acting on the system, and we want to see what kind of effects, if any, what kind of effects with the two observers will see. Right? So let's call this as O prime. So container is O prime. It's a non-inertial one, and my inertial one is O. Right? And now we can try to see what happens. Okay? So again, now if I have hung it, now normally I know that if this container would have been stationary, right, just like in your lab or in your room, if you hang a simple pendulum and do not give it any motion, then it simply hangs vertical, right? So we know that in a stationary system, the gravitational force is balanced by the tension, and the pendulum is in equilibrium, or is basically stable, hanging vertically down, right? We are interested in looking at the same situation when the container is actually accelerated with this acceleration A, right? And so let us see. So in O, so from the point of view of this frame of reference O, what are the forces acting on the system? So forces are, well, gravity, that's a physical force, and that's actually the only force which is going to act on the system. So gravity and its effect will be basically mg. I'll call it Fg, right? There is also a tension in the spring. Let's call it T, right? And we'll look at like how it points and all that. And there is acceleration, right? So the state of system is changing because the container itself is moving. So for an observer here, this pendulum is not stationary, right? It's also moving along with the container. So when I measure it from there, the pendulum or the mass m has an acceleration which is same as that of container. So it's moving with acceleration a. I can balance this out. I can write down my F equal to ma Bohn equation by drawing these vectorially and then looking at the relations. So since we know this problem, so of course the system is going to be different from the one which is not moving. So it's not going to hang vertically, right? So normally what will happen is the pendulum will have a different orientation, right, with respect to vertical, and that will be balanced by the tension T. So let's say this is my T. Acceleration due to gravity, or the force of gravity, is always acting downwards, vertically downwards. So that will be mg, and this mass will have motion in frame O, which is m a, right, where a is the acceleration of the container. So this is my vector diagram for this, and if I say that this angle is theta with respect to vertical, right, then I can write down T cos theta will be the vertical component of this tension will be balanced by this mg, and the horizontal component, there is no other physical force to compensate for this horizontal component. So that means because of this thing the pendulum is going to move, and yes, we know that from looking from here we will see the pendulum moving, right? The position of pendulum is changing in my coordinate frame O, and this will be simply equal to M A. I mean not the vector now because they are writing components, so this will be simply M A. Using these two, we can see what will the orientation of the pendulum as seen from O, right? So you can write down this angle theta as A by G, right? So the person who is standing here, right, looking at this pendulum hung vertically down to begin with in that container, as soon as the container starts to accelerate, a person sitting here, an observer sitting in this reference frame, is stationary with respect to ground, and the container accelerating with acceleration A, will see that this string makes an angle theta with the vertical, right? And the magnitude of that angle will be simply ratio of the two acceleration, the kinematic and the physical acceleration to gravity. Okay. What about the tension? Now, since the orientation is different, if it is vertical, then we know that tension is equal to mg. Now, it is not the same. It's actually in a different orientation. So, with respect to O, the tension T is then basically, this tension, if I can square and add, will be G square plus A square M. Right? So, the tension is also different. So, motion of the system will lead to a different tension in the string. When we are making the observation from this reference frame, we still know that there is a physical force, gravity, and there is a kinematic correction because the entire pendulum is being moved. It's not a static pendulum. We are not looking for the equilibrium of a pendulum in stationary position with respect to this frame of reference O. What about O prime? So let's say the observer now sits in the container. So the observer himself, herself is also moving with acceleration A because I am sitting inside the container, right? So inside this container, I am sitting, the container is accelerating with acceleration A, and I hang a pendulum. And now inside that container, I want to see what happens to that pendulum, right? So inside that container, since I am moving with the container, right, I am actually not going to change my position. And the pendulum is also not changing its position. At any given point, if I try to measure sitting here, at any given point in time, if I try to measure where is this pivot point, let's say let's call it P prime in this frame, where is that pivot point? The pivot point is same, right? The pivot point does not change, right? The bob is also not moving. It's not that the bob is suddenly accelerating with acceleration A, because both are in the same reference frame, right? If that is the case, will I see this pendulum hanging vertically? And if I see this pendulum hanging vertically, then the observation of a static observer are different from the observation of a moving observer, right? But it's the same physical pendulum. So normally that will not happen, right? So let us see what kind of forces now I am going to see when I am sitting inside the container, right? And recall the analysis that we just did in connecting an inertial frame with a non-inertial frame, right? From the point of view of O prime, right? The forces are tension T, mg, right? And a fictitious force, right? As we saw in the previous analysis, somewhere here, a fictitious force, right? And the equation of motions are, since the mass is stationary, there is no acceleration of the mass. That means, if this is theta, then the vertical component, T cos theta, and the horizontal component, T sin theta, are exactly balanced by the fictitious force and the mg, right? In this case, we had a motion of the mass m with acceleration a because there was an unbalanced force T sin theta when looked from this reference frame. In the reference frame of the container O prime, there is a fictitious force, again equal and opposite to this force as we saw earlier, fictitious force which is going to balance this T sin theta, and the vertical t cos theta is going to be balanced by mg. So again, for the exact same system, we have all the force balance, and then from the point of view of O prime, there is no motion of this bob, right? So the bob will still look slanted, it's not hanging vertically. However, it's not going to change its position, right? When you measure, so from this origin, its position will remain constant, the pivot position will remain constant, and again we can write this down as t cos theta is equal to mg, and t sin theta will be then equal to ma, which is coming from the fictitious force. So we'll get the same tan theta as a by g. We'll get the same tension, so be it to measure from here or from inside the container, we'll measure the same quantities, a square plus g square. However, the only difference that will arise is in the interpretation of these results, right? So the person sitting at ground, not moving with the container, will say that there's only force of gravity acting, right, pulling it downwards, but since the pendulum itself is being accelerated in the positive x direction, right, the resultant orientation, resultant force in the spring, the resultant tension is sum of vector mg and vector ma and points in this direction. So the pendulum is slanted, right? A person sitting inside the container again will see the pendulum being slanted with tension equal to this and the angle equal to this, right? So you also say that yes, my pendulum is slanted now, it's not vertically down. However, he or she is not going to assign that change from the vertical position, equilibrium position, as due to motion of the frame, because I am sitting in that frame. So for me, there is no experiment which can tell me if the frame is in motion, right? How do we know that if something is in motion? We measure its position at different times, and if that position changes, that means there is a motion. Sitting in this frame, inside this container, I can do all sorts of measurements and will not be able to figure out any change in the location, right? If I take one corner of this container as origin, as 0, 0, 0, then any other point in this entire container, including the location of the mass and all that, will remain exactly the same, right, in time. So I cannot say there is a motion in the container. However, I still see the pendulum being tilted rather than hanging downwards, and the way I will interpret it, or the way a non-inertial observer will interpret it, is that I know that there is a force of gravity which acts downwards, so I expected my pendulum to be hanging vertically down. However, it makes an angle theta with the vertical, and that means there has to be another force which is pulling it backwards, right? And that pulling it backwards force is the F fictitious. So for an inertial observer, the state of the system is because of the motion of the system plus the physical interactions of the system. For a non-inertial observer who is part of the system, the change in state or the state of the system is because of the physical force as well as another force to which we cannot assign a physical nature because we know that there are only so many forces, right, or fundamental forces. So a fictitious force, however, result of both of these will be exactly the same because the actual system is not going to change, right? Just because you are looking from different points of view, the behavior of the system will not change, but the interpretation for that behavior will be different for different observers. Okay, so anyway, this example is given in the book also, so you can go and look at it. What we have done here in trying to explain this behavior is also state a very profound principle in mechanics with respect to this coordinate frames or references, right? And that is the principle of equivalence. Principle of equivalence. And what this principle of equivalence says, so of course, we will not discuss it here any further. I just make the statement and maybe discuss a very short example. So what this principle of equivalence says is that observations or measurements in a non-inertial frame are same as the observations in an inertial frame plus effect plus some plus some fictitious force, right? So for example, the effect for example, we discussed this container problem. So for a person in container, the position of the pendulum being tilted in one direction is described by effect of the physical force present in the inertial reference frame mg and a fictitious force as if in the inertial frame instead of accelerated motion, the container is still stationary, it's still inertial reference frame, but with the addition that there is a fictitious force, F fictitious, acting opposite to the actual motion, right? Okay. So this is the principle of equivalence, and this is mostly cited or mostly discussed in terms of equivalence of gravity with uniform acceleration. So the most discussed or cited example, which is very simple, is that suppose you are in a so equivalence of gravity with uniform acceleration in, very important, in localized space. So not in the entirety, right? Because once you take a larger and larger system or larger space domain, then there could be there could be reasons to say which frame is actually stationary and which frame is actually accelerating, right? However, for a sufficiently localized space, for example, let's say I am sitting in a closed room, right? Let's say in this room, or normally quoted as in an elevator. So if you are in an elevator, right? Let's say I am in an elevator and I feel normal, like in the sense that I am normally the elevator is accelerating upwards or downwards, you don't feel anything. So if nothing is happening, then we normally say that no, I am the elevator is not moving or my room is not moving. I am still on the ground, right? So Earth is the fairly localized reference frame. I am still on the ground and I am simply being pulled down by acceleration due to gravity, right? That's why I cannot just fly off. I am stationary or normally hanging, standing vertically, upright. Right? Okay, this is exactly the same situation. You will not be able to, we will not be able to differentiate. Now, if suppose the elevator, rather than being in on ground, so well, simple. Rather than being in ground, if the elevator is in, let's say, space, free space, right? So without, not near a planet or not near a star or something, in free space, whereas there is no gravity and accelerating upwards with acceleration A, which is equal to acceleration due to gravity, right? So in terms of numbers, here I am feeling a force pulling me downwards with the acceleration due to gravity equal to 10 meters per second square. The situation will be exactly similar if in free space I am still sitting in the elevator, and the necessity of sitting in an elevator or in a closed space is so that here also I cannot see outside to figure out if the elevator is going down, then the wall is moving, the elevator is going up, then the wall is moving down, or the trees are, I am going above